today I need to do, am I okay? How far over can I go?
About right there.
Okay. Today I want to do summation. Sigma, a capital sigma. How many of you are familiar with that? 3 or 4 of you, and then there's going to be some of you that haven't seen it before, and then there'll be some of you that might have forgotten it. And I want to do and I'm going to just write it, and you tell me if I need to say anything else about it. Make sense to you? And this is, the N is called the index. And what that says is, start at n equal 1, substitute every whole number from 1 to 3, including 3, in, and add them up. That's what it says. And that's all. That's all. Questions?
Can you repeat that one more time?
Sure. It says substitute one at a time every whole number from n equal 1 to n equal 3. That sounds like 1, 2, and 3 to me, doesn't it, you? And add them up. That's all it is. That's all it is. So, this time, do you agree? Everybody agree? I just wanted you to think. I am going to fill that hole in, but I wanted you to think about it. Can you see what I'm about to do? It says start with k equal 1. So I put in 1, then k equal 2, and then k equal 3. And what did I say the last step was? Add them up. Anybody seen any rocket science yet? Okay? So, did you notice I switched letters? I did that on purpose. Does it matter? That's just an index, huh? And that is if I want to count, and I have to count on my fingers, I can count 1, 2, 3, or I can count 1, 2, 3. I could use either hand, with my hand being the index. So it doesn't matter what it is, okay? It's a handy way of adding things when there is a pattern. And we need it in calculus. We need it in calculus. That's why I'm doing this. In Cal 3, chapter 10, is everything we do in chapter 10 has a summation sign in front of it. We're about to use it right now to develop the integral, and that's why we have it here. Let's see if there's a problem in the book that I'd want to work. They did they did this one. I have all of these fine slides that I can show you. However, I can't get to them. Suppose that I had this. I don't want to go starting trouble. That's a 2. And if another point to make is, there are 2 ways I can view that. I can say that the I squared goes with the summation, or I could say that the whole thing does. Which one is correct? Which one's correct?
Both of them.
Nope. Which one's correct?
It's the whole thing.
It is like if I had 3x plus 1. Does the 3 go with the whole thing, x plus 1? Or does it go with just the x?
Just the X.
Well, there's no parentheses. How do you know? Yeah, multiplication goes with you multiply within a term, right? You go to the next plus sign or negative sign, huh? But a sum, isn't a sum, that sigma, is that not a bunch of plus signs? Is that right? So what I'm telling you is, unless, if I did not specify, then that sigma goes with the I squared. So what I want you to notice is that this would be equal to, see if you agree with me, this is 2 squared plus 3 squared plus 4 squared plus 2. Do you agree with me?
With the parentheses there, yeah.
Hmm?
With the parentheses there, that would be right. Right?
Say again,
With
Spencer.
the parentheses are separating the plus 2, that would be right, I believe.
Yes. Well, what I'm telling you is if there are no parentheses, it's understood that the sigma goes to the first plus or minus sign only, meaning the first term. Okay? And that looks like 4 plus 9 plus 16 plus 2, which is 13 plus 16 is 29 plus 2 is 31, right? Agreed? Now what I really meant to write was this. Now, you tell me, how many plus 2's am I going to have?
4.
2, 3, 4. 3? So what that tells me to do, I'm going to write it and give you a chance to look at it and see if you have any questions. Does everybody agree? And do you see that that parenthesis says, take the 2 with it? So be careful. That's number one, be careful. This is easy stuff. And rule 1 of survival in calculus is, don't make mistakes with easy stuff, because there's hard stuff out there, and save your mistakes for that. Don't make mistakes for easy stuff. Everybody okay with the difference? Questions? What I want you to notice now is, and this was the point of starting this, is I think that this is equal to I think that those 2 are equal. Let's see. This is 4. That's 4. Let me switch colors. I want to get a number. This is 4. That's 9. That's 16. That's that. That's 29. Is that right? And then 6 is 35. Okay. I want to get a number because I'm going to do the same thing here and get the same number and convince you of that. Okay. So I think that this, I'm tired of these, putting these things back on. I think this is equal to 4 plus 9 plus 16. Is it okay if I haven't promised you, I need to go ahead and do it? What's the promise I make every class, for those of you that have had me? I won't get in a hurry and skip steps. I tend to do that, and the very step that I skip is the one that you wished you could have seen. So if I do that, stop me, and I'll do it right. 4, 9, 16. See how little time it took me to write that? That's why I don't skip that. Okay? And then, now let's think about this. What does this say? This says start with 2 and put 2, then 3, then 4 in the place of I and add them together. What's the problem? No I. No I? So if there's no I don't have a place to put it, but I do have this 2 out there, don't I? Is that right? So what I'm going to write is and so there's no doubt this 2 comes from I equal 2. This 2 comes from I equal 3. And this 2 comes from I equal 4. Everybody okay with that? And then what I think I've done is this much of it goes with this, doesn't it? Agreed? And this much of it goes with this. And what I want you to notice is do you see any difference between this and this, except the order of them? Everybody? So would you say, that is, Spencer, that's Justin talking. He would always, after I say something, he would say, so, and then he'd restate it. So would you say that is that a true statement?
Sorry.
Is that a true statement?
Yeah, distribute.
Yeah, it is very much like the distributed property. I'm not going to tell you that it is because it's really not. The distributed property has to do with multiplying, right? And we're not multiplying anything, so I can't say that. But if you happen to notice that and wanted to think that, you could. Are we all okay with that? And for my audience that is listening in, that says, if adding inside the parentheses, we can break it into two sums and handle each separately. That reminds me to push this button and see if anything happens. I think it's deader than I nearly said I think it's deader than it was before. The problem with that is, number one, I'm not sure that deader is a word, and how can you be more dead? But we'll leave that for another day. Everybody okay with that? Now, would you agree? Would you agree? If you can do what?
Hear the sound, B-52.
I'm sorry.
Yeah, B-52 is going over. So it's like, what's going on?
Now,
Or something. Anyway, go on.
would you agree that I could say or subtracting? To me, subtracting is adding a negative number, is it not? So oftentimes in fact almost every time, I will mean adding or subtracting because I think of it as adding. Okay? All right. Now let's do another one. Where to put it? I think I can erase these. There is a class that you will take called differential equations, and if you hadn't heard about it, you will. You'll hear me talk about it. You'll hear some of my students talking about it. You'll hear some of the ones that will be taking it a second time talking about it. And erasing like that reminds me of in the old days with chalkboards. I taught differential equations in a room that had a chalkboard in the front, a chalkboard down the side, windows in the back, and a chalkboard on this side. And I started at the far end on one problem with summations in it, with summation like this in it. And I went all the way around the room and started erasing back up at the top before we finished the problem. And these summations, my point is, these summations can, as bad as that was, they save you an awful lot of work because you can talk about a string of things at one time. All right, I got another thing I want to talk you into. And that is this. Now I've got do better than that. Is that, do you think that that is 3 times 2 plus 3 times 3 plus 3 times 4? Do you think?
I assume, yes.
Say what?
That's what it looks like. I mean, from the summation.
Yeah, remember our rule for our definition of summation, and that is start at 2, put every whole number in for the index, and then add them together. Isn't that what I did? Okay? And that looks like 6 plus 9 is 15, plus 7 is 22, huh? Is that right?
It's 12.
Now,
That's 27.
7 and 7, 12.
do what now?
3 times 4 is 12.
It
You said
is.
7 instead of 12.
Let's see.
27.
6 and 9 is 15, and 12 is 37.
27.
Thank you.
27.
I was just like, yeah.
27.
Very good.
I'm going to do that all semester. Number 1, you see all this gray hair? You'll be there one of these days. Number 2 is, I don't have the luxury of thinking about what I'm writing. And that is, while I'm writing, I'm thinking about the next thing I'm going to tell you. Do you follow? So all I can tell you is, please stop me. Please. The first thing I'll say is thank you. I think I said it then, didn't I? Thank you. The further you let me go in a problem after I've made an arithmetic mistake, doesn't that just compound it and make it worse? So I'm asking for your help. I can't. The only way that I could keep from making mistakes is if I had prepared notes and read them to you. And I don't believe either one of us, any of us in this room, want to do that. Huh? That would be a miserable calculus class. So, help me. Okay, now,
Doesn't want to work for you, does it?
now, then I used it a minute ago. I guess I can't leave them open like that. I get worn out. Taking these blasted covers off, but I guess I'm gonna do it. I'm a old chalkboard man anyhow.
Why did we do away with the anyway?
Oh, the dust.
Is that the Maddox cake?
No. It's not mine, okay.
It's not.
I erased.
You don't get looking for those in there either. I get one. Oh, well.
Why can I do that?
Because it's constant.
do that?
Because it's constant.
What?
It's a constant.
It's a constant, very good, I just didn't hear you. Take a look at this. Could I not factor a 3 out of every term? And what I want you to notice is that's nothing but the distributive property, isn't it? Everybody agree? So then I think that's the same thing as 3 times 2 plus 3 plus 4, which is, all of that is 9, which is 27. So do you get the idea? Okay? Questions? Now let me look, see if I left anything out. Okay. With that, I've said all I need to say. All you need to do is practice a few problems, and that would be section 5.2. Just practice, and all that does is give you a few problems to get you comfortable with it. I'm gonna have to erase this. Everybody got it? Now, back to business. This ought to be good. This ought to be good. I have to start drawing now. You remember this one? That's too big. I don't need it that big. X is 0, y is 0. If x is 1, y is 1. If x is 2, y is 1, 2, 3, 4, 2, 4, 3, 9, 3, 9. You remember that one? And what I want to do is, I want to talk about the area from x equals 0 to 1, 2, 3. I don't have room for 16, so I'll just do right here.
Drop on you again. Shots.
That's 3 points. That is 3 points. It's also my last blue marker. Okay, what I want is, I want that area. And what I'm going to do is, I'm going to do the midpoint rule. There's a midpoint. There's a midpoint. And there's a midpoint. Follow what I'm doing? So I'm going to make some rectangles using the midpoints. 1, 2, and then here. And then here. Everybody agree? And if that's 3, then this midpoint is the point 1/2, and this curve is y equal x squared. Do you remember that? So the y value of that is 1/2 squared. That looks like 1/4 to me, doesn't it, you? And this one, this midpoint is the point 3 halves, 1 1/2, 3 halves, 9/4, And this midpoint is the point 2 1/2, 2 1/2, which is 5 halves, right? 5 halves, 25/4. Everybody agree? And the area, our approximation of the area is equal to length is equal to the area of region 1 plus region 2 plus region 3. I've got a point, I'm not reteaching what we did last time, that's just, I've got to set this up. And for every one of those, these, it is length times width. Don't you agree to that? Only the length, I'm going to call the width the x-axis, okay? And the length is what? How high is it? For any point in the plane, but in particular in quadrant 1, any point I want to put out here, how high is that point off of the x-axis? I'm looking for you to tell me why. Whatever the y value of that point is, isn't that how high it is off of the x-axis? And in particular, what I wanted you to tell me is that under what circumstances, I'm going to pick on that, under what circumstances is that true?
It's the same thing.
It is indeed, always. I picked Matt because he's had me before. You can't have me for a math class that I don't say that 1,000 times a semester, right? Y equals f of x. One is their first name, the other one's their middle name, and it's the same person. Anytime I want to, without explaining, without telling you what I'm doing, I can change those two and I don't owe you an explanation. Can we agree on that? Okay? So in particular, what I think is that R1 is equal to delta x, and we'll talk about that in a minute, times f of 1/2. What do you think? What I'm trying to say on is the f of 1/2 business. Isn't that exactly how we got 1/4? Isn't that right? Is I took this number, and I substituted it into the original equation. Do we agree? Okay? So, you'd agree that that is the 1/4 that we use. Now, what I did is, when I got ready to mark those off, I marked them off as 3 rectangles. Could I have used 6?
Yes.
And in fact, wouldn't it have been better to use 6? And wouldn't it been a pain in the wherever to use 6? Could I have used 36? And wouldn't it have been better to use 36? And wouldn't that pain have gotten worse? But you follow what I'm saying, huh? So what I'm going to do is, well, I broke this distance on the x-axis. This distance on the x-axis, I broke it up into 3 equal parts, right? And if this is 1, 2, and 3, and the distance from this point to this point is what? 3. So I take the distance on the x-axis and I divide it by the number of rectangles. And doesn't that give me the length of each one of these rectangles, the width of each one of these rectangles? Do you agree? And they stay the same because I marked them off equally, right? Everybody agree? So I'd suggest to you that I'm going to call that delta x. Now, don't I have the width of every rectangle? And it doesn't change because I divided them into equal parts. By the way, to do what I am about to do, it doesn't have to be equal parts. I see no reason. It does not change the correctness of what we're doing to let them be equal. And it's a lot easier for you to grasp if they are. So I'm going to just always do equal parts. And as a matter of fact, every one you saw me do last class period was equal parts. Agreed? Okay? So, now, in this case, my delta x is equal to the distance on the x-axis. I'm talking this, right? I think that's 3. And how many parts did I break it? How many rectangles? 3. And 3 divided by 3 is 1. So now R1 is equal to 1 No, it'd be 1/4, wouldn't it? Everybody agree? And R2 is equal to delta x times f of 3/2. Agreed? And delta x stays the same, so isn't that 1 times 9/4? You get the idea? Everybody? Everybody's okay with delta x staying the same because I made it that way. I wanted to keep this simple. Okay? All right. Now, I'm gonna have to erase this. I'm trying to stay sort of in the center because of the camera. Can I erase that now? Okay? Now here's what I'm going to do. I want n to be equal to 36. And I don't want to have that particular pain that I was talking about. So what I'm going to do is, I'm going to use sigma notation. I'm going to say that, first thing I'm going to say is that delta x is equal to the length on the x-axis. That's still 3, isn't it? All we're doing is dividing it up into 36 rectangles, right? So that's still 3 divided by the number of rectangles. Okay? And I think that then is 3 over 36, which is 1/12. Agreed? So now I think that the area is equal to, delta is equal to isn't that length times width? Now, the obvious question is, what is C sub k? Isn't that the question? C sub k is the center of each rectangle. Isn't that exactly what I did right here? Isn't that exactly what I did right here? Do you agree? So all I'm doing is I'm saying that C sub k is the midpoint of well, hang on, I'm making this up as I go along. There's 2 ways I can do that. Give me a second. Here's what I'm doing. I have now given these names. Here's where I need another color marker. I guess I can use red. I have now, this point is x naught, x sub 0. This point is x1. This point is x2, and this point is x3. And all they are is, all the x's are the points on the x-axis that correspond to the rectangles, right? Would you agree? And in fact, for any x sub k minus, if for any x sub k minus x sub k minus 1, that is delta x. Is it not? What I'm saying is, if I take x of 2, whatever it is, and subtract x1 from it, isn't that just the length where I'm marking it with my finger? And didn't we make each one of those lengths be equal to that delta x? Do you agree? Everybody? Okay? So, now what we have is, now we can handle as many as we want. Right? And all I'm saying is that c sub k is equal to c sub k, that looks like c sub r, doesn't it? C sub k is equal to, see if you agree with this, x sub k plus x sub k plus 1 over 2. What is that? What formula is that called? That's exactly the midpoint formula, isn't it? Didn't you learn in high school that if this is the point 1, this is the point 3, 1, and this is the point 7, 3. Didn't you learn how to find the midpoint right there? Add the x's together and divide by 2. Add the y's together and divide by 2. Isn't that the way you do it? Well, isn't that what I'm doing? Does everybody agree? Oh. Dr. Collins, did you flip the light switch?
No, what happened, we're being invaded by alien snowmen from Mars.
Okay. Well, wouldn't you guys agree they would likely come to a calculus class first?
They would.
Can you see the board?
I've got a blue mark.
That was a rhetorical question. That means that I'm going to keep on going whether you can see it or not, because I can see it perfectly. Okay? Are we all right with this?
Yeah.
Okay? So now, do you see how I have a tool for breaking it up into as many parts as I want? Everybody? And in particular, what I told you the other day, would you agree that the larger n is, the better off we are? Would you agree with that?
Yes.
Everybody?
Yes.
Okay? What is the largest that n can be? Indeed it is. Indeed it is. And in particular, if I want, I'm going to have to erase again. What do I erase is what I want to know. I'm just going to try to squeeze it.
Is anyone else having trouble with the glare?
All it won't matter anyhow. Sorry about that, y'all on the camera there. We lost power in the building, if you're wondering what's happening.
Do we have the fluorescent markers?
Yeah. Now, what I want to know is, no matter how big this number is, it's still just an approximation. Do you remember the error deal? It's still just an approximation. But if I take the limit as n approaches infinity, Calculus 1 students you had to have enjoyed that first chapter in Cal 1 on limits. That was lots of fun, wasn't it? Back to that pain I was talking about a minute ago. I want to take the limit as n approaches infinity of wait a minute. So all I'm saying is that I'm going to divide it up into n rectangles, but then I'm going to let n be equal to infinity. Huh? And what I'm doing is, let's just say I start right here, and I'm going to walk from here to here, from one end of that table to the other. Huh? And I'm going to walk half the distance every day. How long will it take me to get to the other end? How long?
Technically, you'll never get to it.
You'll never get there. Agreed? You'll never get there. But again, back to the concept of limits, I will eventually get so close that it doesn't matter. Is that right? And is that not the concept of a limit? So there's no such number as infinity, but when I let it get to be a gazillion, trillion, 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 that's close enough. Okay? So now what I have done is I have divided this up into an infinite number of rectangles, huh? And it's sort of like a pie, and that is, theoretically, it doesn't matter how many people come for Thanksgiving dinner, everybody can have a slice of pie. But those slices get mighty thin, don't they? And that's what I'm saying about these rectangles. They get mighty thin. Okay? This is called a, what's the name of it, Ed? Do you remember?
Well, paradox.
Riemann sum. A Riemann sum is what that is. And that is equal to the area. Yes.
I understand the concept, but where does infinity come into that equation?
I raised my n, didn't I? Right here. I said as n approaches infinity. I'm sorry.
Oh, okay. Yeah.
Sorry. I guess I got off on a tangent as opposed to a secant. Okay? Questions? Now, I got two things to do. Number one is, I forgot something I needed to do about sums. It hit me. I think what I'm going to do is I'm going to stop right here on that Riemann sum and come back to it and do the thing I forgot, okay? All right? So, here's what I forgot to tell you. I expect you could have figured it out, but it hit me a minute ago. And this is telescoping. That's my name, not the book's name. I feel no obligation to follow the book, though I really do try not to confuse you. Telescoping means this. If I have the sum of n equal 1 to 4, I think I'll make it light on myself, n equal 1 to 3, is that of n squared. I think that's 1 plus 4 plus 9. Do you think that?
Yeah.
And I think that's 14. What I want you to notice is this. I changed the values on the index, didn't I? Do you agree? And I also changed what was inside, right? And I, in effect, telescoping, you know what a telescope is. You pull it out like that, and you look through it. And the reason in my day that we called it telescoping is because I'm stretching it a little bit. I'm changing the boundaries a little. But look what happens. Look what happens. If n is 0, don't I get 1 squared? If n is 1, don't I get 2 squared? And if n is 2, don't I get 3 squared? Do you agree? And that is 14. And that's what I call telescoping. That means that I can change the values of the index as long as I do a corresponding change inside the parentheses. And here's the way I remember it to this day. I'd encourage you to use this. If the index goes down, and it did, didn't it? Do you agree? It went from 1 to 0 and from 3 to 2, huh? If the index goes down, then what's inside the parentheses has to go up. Follow? Everybody? All I'm saying is, if I want to start at 0 instead of 1, I went down 1, so inside the parentheses, I have to go up 1. Follow? Everybody? And we're going to use that over and over and over again. It's called telescoping. Or re-indexing. I don't like that as much as the old telescoping. It's really not doing anything. You really haven't changed anything, have you? Agree? Everybody okay with the concept? I probably could have gotten away with just letting you figure it out with the homework, but I don't like to do that. And that's why I felt like I'd better go back and do it. Okay? Questions? All right. Now back to calculus. Now, for people that have had me before, you've heard this one too. Math teachers accuse math students of being lazy. We really do. We talk about you. We accuse math students of being lazy. However, in order to be a math teacher, one must first have been a, therefore math teachers are, bingo, guilty as charged. So what I'm telling you is, I am not going to write that every time. I don't want to write that every time. So I'm going to do a shortcut way of writing it. And the shortcut way is, I want something, the Greek letter sigma, you think of as the equivalent of a capital S, don't you? For those of you into Greek letters, is that right? So what I'm going to do is, I think I would have done it in blue. I really would have done it in blue. This is a blue kind of thing to do.
Miles, I have a blue marker here, if anybody can notice it.
You got a blue marker, Ed? Toss it to me. I was an old first baseman. I should have been able to play that
I
one.
sure don't have any in my classroom.
But the knees were better then than they are now. I want to use something that would remind you of a sigma. And what I'm going to use is not a capital S, but a stretched S. Is that a capital S that I grabbed each end of and pulled? And so help me, for the rest of your life, when you see that stretched S, I want you to say that's nothing but a sum. That's nothing but a sum. And that is the sum from 1 to infinity of f c sub k dx. And what is that called? An interval. That's called an interval. That's an interval. And all that says is, I am, and I'm going to take these off because we're not ready to deal with them yet. All this says is that I'm dealing with how many? How many? An infinite number of rectangles added together, length times width. And in the place of delta x, I use dx. It is it not, as though I was changing this problem from Greek to our alphabet? The sigma becomes a stretched s, and the delta becomes a dx. Okay? And so help me, that's where integrals come from. Integrals are nothing more than a whole bunch of little rectangles added together. And how much is a whole bunch? An infinite number. And integrals came into being because lazy mathematicians didn't want to write this every time. And God bless them as far as I'm concerned, because I wouldn't want to write that every time. But it means nothing more than that. So here is the first time I've mentioned intervals, right? And this whole semester is about intervals and evaluating intervals. This whole semester is. From here on, that's what we will do. But I want to make sure you understand there is no mystery to this. It's nothing mysterious. We've been adding little rectangles since last week, and you've got the idea, and now all I'm telling you is add an infinite number of them, and instead of writing that out, the limit of the sum is in as k approaches equals 1 to n, where n goes to infinity, and so on and so on. You just write it like that. That is all it is. That is all it is. Don't make anything else out. Okay? And every one of those principles that I used for sums, you know, like if you have a constant, you can pull it out front. Do you think you could do that with an integral?
Mm-hmm.
Sure, because the integral is a sum, isn't it? It's just a sum. I'm just too lazy to write it. Is that right? And that stuff about if you got parentheses and you got two terms, can you break it into two different intervals? Absolutely, because I'm still dealing with sums. So, don't go telling your friends that Cal 2 is this easy. We want them to think it's hard. But I'm telling you, all it is just adding little rectangles. That's all there is to it. And I want you to never forget it. Nothing mysterious about it. Nothing mysterious. Okay? You also learn, well, let me stop for a minute, catch my breath, and let me draw a little. Bad as I hate it. Gosh, I could use that projector. This is the way I used to teach calculus, and it was not fun. Right there, isn't it? Here's our old curve. Same old one we've been doing without that little wrinkle in it up at the top. Now, if I wanted the area between 0 and 3, which we did a minute ago, if I wanted the area, stinking combat, wouldn't it, suppose I wanted this area. That's the area A. I think that if I gave you long enough to think about it, you would tell me this. I'm not going to give you that long. I'm going to write it and see if you agree. I'm taking this distance 3 and I'm breaking it up into an, 0 to 3, isn't it? Right? Everybody agree? I'm taking that area, I'm breaking it up into a whole bunch of little bitty rectangles, and then I'm adding them up. And a whole bunch is an infinite number, right? So what I'm telling you is, this says what we've been doing so far this semester, does it not? And doesn't this say use the midpoint? You remember from last time, you could either do the left end, you could do the right end, or you could do the midpoint. And doesn't that C say the midpoint of every interval? Okay? Alright, now, suppose that I defined a new function. A new function,
Maybe not.
Watch the heat ray, Mars or whatever.
Donna scared the Martians off. We're so far now, I think I'm not gonna turn it on because it may be going back off again.
Just see if it'll turn on though. You know it's bothering you. Is it bothering me?
What is that? This is the area from 0 to any point x on the x-axis. You get the idea? What I'm telling you is, if this is from 0 to 3, suppose I just wanted to go to 2. Wouldn't I change that to a 2? And all I'm telling you is, this can change depending on how big you want the area on the x-axis to be. The width. Everybody okay? All right. But you know a relationship between f of x and little f of x. You know a relationship between that. You learned it in Cal 1. What is it? What?
Derivative.
Derivative. Very good. Or antiderivative. Huh? And that is, if we're going in this direction, the relationship is f prime of x is equal to what?
I'm actually reading that.
That's the relationship. It is that last section that I know Ms. Hardy covered, because she and I talked about it, called antiderivatives. I'm not going to say, well, you're supposed to know that and go on. I'm going to do a little review of it. But what we found is that big F, the derivative of big F, is indeed little f. So what I'm saying is that you can take the derivative of the big F outside the integral and get the little f inside there. And then in the other direction, in this direction, it is f of x is equal to and this is, f is the antiderivative. And the antiderivative is going backwards from taking the derivative, right? And you should have done problems like that in Cal 1 of that. And in fact, I saw your final exam, and Ms. Hardy had something like this on the final exam,
You missed it.
didn't she? Ms. Hardy, for those of you, Ms. Hardy just taught Cal 1, for those of you that haven't had it. But I saw her final exam, is that right?
That's right.
And doesn't this say in words, doesn't this say, what do I take the derivative of to get x squared? And when you answer that question, you have evaluated that interval. Is that right? And let's see, to take a derivative, you multiply by the exponent and subtract 1 from the exponent. Now we're going to do that in reverse order. What's the reverse of subtracting 1 from the exponent? Add 1. What's the reverse of multiplying? Dividing. Huh? So do you see, all I'm doing is changing direction? Everybody agree? So what I'm going to do is I'm going to add 1 to the exponent. Isn't that x cubed? And then I divide by the exponent instead of multiply by it. And the nice thing about it is you can check your answer. How do you check your answer? Take the derivative of that. What's the derivative of x cubed over 3? Bingo. Everybody agree?
Smart.
Questions? Questions? Yes. Travis? Yes. Yes.
You took points.
I'm gonna get to that. But for right now, is that look pretty easy to you? Okay. Now, what do you take the derivative of? I know that's not good English. What do you take the derivative of in order to get the cosine?
Sine.
Looking pretty easy to you? It is. It is. But let's never lose sight of what that stretched S is. That stretched S is the sum of a whole bunch of little rectangles, is all it is. Okay? Now, Travis said, don't you add a constant? Here's my question, one more time. Tell me how to check your answers. You take the derivative, I take the derivative of this, and I had better get this. Is that right?
Right.
Well, what would happen if I had here plus, I'm not going to try another 3-pointer, plus 2.
Do just throw away.
My question is to you, would that work?
No.
It would, wouldn't it? Because when you take the derivative of the 2, you get 0, and you wind up with x squared. Huh? Agreed? Okay? As a matter of fact, any number that I stuck on the end there would work, because it'll go away. So what we're saying is that instead of just one answer, I get an infinite number of answers. In fact, any constant out there. And do you remember, and I told Ms. Hardy to get after y'all about it, and to count off if you don't put a plus C out there. And my markers are falling fast. Let me find your blue one. That blue one will work. And I'll bet she counted off in Cal 1 when you took antiderivatives if you didn't put the plus C. Huh? And some of you had me, some of you in this room had me for Cal 1, and I know for a fact I counted off. Okay? So in each case, you do plus C. Okay? Now, these are called limits of integration. Those are called limits of integration. And anytime, here's one to write down. Write that down in your notes, if you can read it. Save you some points on tests and save me some red ink. If you have limits of integration, you don't need a plus C, because you will only have one solution that works. If you don't have limits of integration, then you always put the plus C. Okay? Now let me look at the book. And catch up. You can now do the 5-3 homework, 5-2 homework. And I'm not ready for you to do 5-3 homework just yet.
Is this all in 5-2 or is it one 5-3?
Some of it's in 5-3, but I'm not ready for you to do, I may be getting ready here in a minute, but. Let me work this again. There's some homework problems like this, so let me work this again. I told you enough to do it. I mean, you know a lot of Cal 2 right now, but I'm going to. Minus 1 to 1 is 5. 1 to 4 is minus 2. Minus 1 to 1 is 7. And this is example 2 on page 319.
All right, be sure that's correct, because you've got the first integral equal to
I
what?
changed the function, Ed. I went
Oh, okay.
from
H
f
of
of
x.
x to
Okay.
another function,
Okay.
h of x.
Okay,
That's why I looked at it twice.
okay.
Dr. Thomas's point is, if this were f of x, I couldn't have it be equal to both 5 and 7, right? But I changed the name of the curve, so doesn't that change the height of the little rectangles? Okay? Now, I'll do this all semester. That's page 319, problem 2. Okay? All right. Given those, they want us to find the integral from 4 to 1 of f of x. A. What happened? What's the difference between what I just wrote and what part A is? I reverse the limits of integration, huh? Instead of going from minus 1 to 4, from minus 1 to 4, is that not going this way? Do you agree? I'm going from 4 to minus 1. So what changed?
The direction you're going in.
The direction. The total length didn't change, did it? The direction changed. And in math, how do you say change direction? The sign, the S-I-G-N, not the S-I-N-E, huh? The S-I-G-N, the sign. Doesn't, in math, didn't you learn a long time ago that positive and negative only mean change direction? Or as we used to say in the military, about face? Turn around and walk the other way? Agreed? Okay? So, I think that this is equal to minus the integral from 1 to 4 of f of x dx.
You put 1 to 1.
Well, thank you.
You're welcome.
I require custodial care in my old age. All I'm saying, doesn't that say I changed the direction? And don't I already know what this is? Do you agree? So doesn't that mean that this is minus a minus 2, which is equal to 2? And just so there's no doubt, this minus sign came from there, and this minus 2 came from there. Are you okay with that? And that's not calculus, that's not rocket science. That is what you learned in high school, that when you change direction, you change the S-I-G-N. Okay? All right. Now they got another one. Wonder if this thing will come it's acting like it. Now they want us to know, want me to find out what is the integral from, this is D, the integral from -1 to 1 of f of x dx. Let me make sure I got that down. Nope. 2f of x, 3h of x. I think so. Somebody check me, did I copy that down right? I'm good about copying them down wrong too. I'm telling you, if there's a way to screw it up, I do it. So y'all just watch me. Is that right? Now, what's the first thing you notice? Yeah, there's two parts. Two parts. So can I break it into two integrals? And I didn't even tell you that, did I? Did I tell you that about integrals? I didn't have to, did I? Why? Because an integral, that stretched S, is nothing but a what? A sum? A sum? And you know that with sums you can do it, right? So I don't even have to tell you that. Okay? And further, what about that constant? When I break it into two parts, what can I do with the constant? Yeah, and I didn't tell you that, did I? But it's a sum. Okay? So what I want you to notice is, I think this is 2 times the integral from -1 to 1 of f of x dx plus 3 times the integral from -1 to 1 of h of x dx. And you knew that without my telling you anything. But let's see, don't we know that this is 5? Do we not? And don't we know that this is 7? So don't I then have 2 times 5 plus 3 times 7, which is 10 plus 21, which is 31. Isn't that good? And you knew that without me even giving you any rules for integration because you knew it was a sum. Questions, anybody? Now can I let you do? You can now do 5-3. If you run into what you can't do, you can ask me about it next time.
dx is on the very top one, you usually put them under dx.
Ooh, look what I did, William. Shame on me. This means nothing unless that dx is there. Because the dx, doesn't that make it length times width? I wouldn't have liked it if you'd have done that. Do as I say, not as I do. Let me see if I've got a network. If I have, we can work on some of you that have time.
Might as well let people know that I'm moving my office this week. If anybody wants to come by, I can help you with right to the carrier's office, and I think Laura's moving to my office, and then I moved to the one closest to the.
Laura doesn't need to be sitting there listening to everything I say all day. She'll want to move again.
Anyway, I'll be available from 11 to 1, and then from
It looks like, so far I can't get on yet. The only reason I wanted to get on is to help somebody log in. All I can say is call that toll-free number that's on there if you have troubles, and they'll help you straighten it out. Wait a minute, is there anybody that's having trouble that has time to stay and let me help you? If you came in late, I need to talk to you and mark you present. This is not a freshman math class where people wander in and out. This is the real one. And I want y'all to know. Having said it, I told you the first day, I'm here. This is school. And that means on your side. And that means okay, let's see if we can get on. I think so.
Yeah, this dude told me some like that you can be like
Anybody else?
lessons and get pulled and like get ask
Let's see if I can get on the internet.
and people are gonna target you. Going to water?
Nope.
And he's like,
No, sir.
Shut up.
Come by and see me, is all I can tell you. Basically, what you're supposed to be able to
Garrett,
do
my purple ball caught me in
is
the
you're
arm bar.
supposed to take
I
your
was like
Dipsy
here, and
email
he was gonna pull it, and so I was
First
like, man, I
name,
want to
last
hit him
name,
enough,
run
like if he
together.
would let go. So
Whatever your
you had it like
Dipsy email.
facing, it's facing your chin because the thumbs
And
up, and so it's like
either
right
the
here,
111,
like when you're trying to
which
pull
I
it,
don't think's right.
like down.
I think
So
it's
he's got me
month,
here, and I'm
day,
like,
and year, birthday.
just like pegging
So
him
he's
off
on the
the
ground,
like upside down. I hold my arm.
So he's
And his legs are
Yeah.
one in front, like one over here, and he's about to pull it
Did
to
you use
there, and
month,
I'm
day,
just
and
like
year?
holding it and being like, what if I hit him
Did you
enough?
use the
If he
one-
just let go, and so like I pushed it like through his hands, like
the
into his
odds
face, and like
are
bam,
you're
and then I was
gonna
like,
use the right email.
and like he still pulled it, but I was like, he loosened up for the, like the third hit,
So,
he loosened up, and I
And
was
then
like,
if that
what
doesn't work,
happened?
I really didn't know.
Can you just be like,